Awesome. Thank you very much. Welcome everyone. I hope you enjoyed lunch. Chilly wasn't too bad, at least I didn't think so. And of course I hope you're enjoying the weather too. The token slide. I'm Will, online, Twitter, Discord, anywhere. Stealthsploit. Co-founded a Cambridge-based cybersecurity company. So when I saw B-Sides Cams pop up, I had to represent quite literally and figuratively. So yeah, I'm a pen tester, red teamer, hacker by trade. Used to be in digital forensics, but then I turned massively offensive, and I also do some pen testing on the side. I've been lucky and humbled enough to have been training and speaking at a number of different places. And this year, I managed to socially engineer myself into helping out Password Village at DEF CON, which was fantastic. Yeah, I've got another job as well, and I help out in various advisory sort of capacities, but that's pretty much all there is for me. Okay, the agenda. So, first of all, who here is either a pen tester, red teamer, generally someone offensive? Brilliant. Who here has password cracked before, has cracked a hash? Even better. Who here really geeks out and loves, obsessive? This is like IT porn for me. Who really loves cracking hashes? Like, really loves it. Fantastic. Subtract that number and I know how many people I need to convert by the end of this talk. So that's where we're going to start. We're not going to be doing anything intro 101 stuff, I apologise. This is going to assume some knowledge. We're going to be getting some weird and wonderful attack chains. Talk about passphrases, specifically delimited passphrases. As time goes on, promoting length over complexity, we need to make sure our secrets are being kept secure. We're going to go into some deep stuff around Hashcat internals and rule buffers and position buffers. I'm a massive Hashcat fanboy. Anyone use John the Ripper? Okay, you can all exit now. Fantastic. It's been great having you in the room. But it's good for what it is, but Hashcat is quicker. And I don't get commission, but I'm a huge Hashcat fanboy. My emoji. See, look, this is what happens when I don't run on my own laptop. That should have been the O in emoji, quite clearly. We're going to look at emojis, Unicode, and cracking hashes with hashes. If that emoji's moved, there are going to be a couple of other things that are out of place, unfortunately, because I didn't have time to vet this before we started. The only primer we're going to drop straight into, though, is masks, kind of 101, because we need to understand what masks do in terms of cracking hashes so that we can understand some of the more complex attack chains that we look at soon. So, a mask is effectively one of these inbuilt Hashcat character sets. We have L, U, D, S, and A. You can see we have a few more over here. We're not going to touch on what these are. L for lower alpha, U for upper alpha, D for decimal, and S for those elusive 33 special characters. We also have A, and when we see a mask with an A, question mark A, it says test all lower, upper, decimal, and special, which accounts for the 95 printable ASCII characters we typically work with. So, if we had an example password of Pwning123, we can see a mask that would absolutely match that password. Clearly an attacker wouldn't know the mask to use, but this is just so we can get start to get a grasp of what masks do. So we can build this into attack chains using attack mode 3, brute force mode, to do either that. We can pass standard in. When we want to test per position character sets that contain either upper or lower, for example, or more than one character set, we can also define up to 4 custom character sets using -1 through -4. In this instance, we can see that we're saying custom character set number 1 will only test for upper and lower alpha characters. So when Hashcat sees 3 instances of question mark 1 in the mask, it's not going to test decimals and special characters, reducing the key space and therefore massively increasing our chances of attack. With the primer out of the way though, let's get into some fun. So I sometimes get asked, how do I do this? Anyone who's cracked passwords might have done masks, you might have done word lists, rules, yada yada, we'll get to that later. But what if I know the start character, what if I know the end character, but I don't know how many characters in the middle? This is there's probably a better way for it, but I call this midway incrementing masks. So we don't know how many is there, but we know the start and end. Hashcat can't, natively do that. But luckily for us, and as we'll see as we go through this presentation, Hashcat is fully pipelinable, and we can chain all manner of things to Hashcat. And here are 2 examples of what we could do to do just that. In this example, we can see the password we've cracked starts with a number. So what we could do is we could create a word list containing 0 through 9. Okay? Easy, job done. We could then use that mask in -A6, which is a hybrid attack mode. So hybrid attack mode is take a word list and then add a mask to it. We could then increment this mask, which means it'll start at here and then build up and up and up until it keeps going. But instead of trying to crack a hash with it, if we write standard out, that's just going to print our candidates to the screen. We can then pipe this back into Hashcat, and then we can append our last known character or known character set as a rule. Now, if we want to go deeply technical on this, there are actually some really important caveats to this. The number of L's you could do here is finite. And this is because when Hashcat uses masks in this sense, in A6 attack mode, we're storing that value as an unsigned 32-bit integer. So 32-bit integers could have of course, store a lot less than a 64-bit integer can in A3 mode. So you're going to get an integer overflow very quickly if you try and test above 7 in this instance. But your testing may vary, and I can, of course, go into more detail offline if people are interested. Okay. Separating the wheat from the chaff. So, expander and print. Who's used expander? Don't be afraid. Who's heard of expander? Oh, okay, I know you wanted to target this. Who's heard of print's processor? Anyone? Okay, so these are very, very cool tools. Very token high-level intro on this. First of all, if you've not got the Hashcat utils, download Hashcat utils. It has a ton of really, really useful tools that you can use to enhance and augment your attacks. One of these tools is called Expander. I've got a couple of screenshots in the bottom right that shows you what Expander does. If we were to give Expander a word, for example, Hashcat, expand it, always unique the output, because it does produce dupes, we can see what it does. It's taken our word Hashcat, and it's chunking this up to a maximum length of 4, because that's what Expander uses by default, but all the letters will always be contiguous in how they appeared in the original candidate. I highly recommend you recompile Expander with 8 or 10, depending what you're after, and you can see you get a bit more mileage. But visually seeing what Expander does will go a long way into showing you how weird and wonderful these candidates can be produced. So this is a candidate generator, okay? Fantastic. That's Expander out of the way. Print's processor has its own repo. Print, again, is a candidate generator, but this is more targeted towards building parse phrases, chains of elements together. And you're going to hear me using elements a lot, because when we talk about a parse phrase, there are a number of elements in the parse phrase. So QWERTY 1, 2, 3, 4, 5, 6 would be a 2-element parse phrase. Okay? You could refer to them as passwords, but as you can imagine, that's going to get very confusing in a talk about passwords. So taken straight from the wiki here, if I was to tell Print's processor, here's rockutxt, because it's a very common, well-known, and very tiny dictionary that most people are aware of. If I say, read through RockU and print me every possible 4-character passwords, these are the only ways you can generate a 4-character password. So Prints will go through RockU, or your word list of choice, and generate every 1, 2, 3, or 4, and mix and match them together until it produces a 4-character candidate. Now, that might seem pretty basic, but when you get into bigger lengths, it becomes absolutely crazy, and you can tell Prints, guess a minimum of 3 and a maximum of 4 elements, and you can build this up to fulfill the requirements that you're after. We'll have a look at this in context very shortly. Okay, one of my favourite slides is just a sea of Hashcat syntax and stuff. These are really cool attacks. So what we're talking about here is, I speak to a lot of pen testers, my company does AD audits, every pen tester sees hashes. People tend to run RockU, they'll run at rules, they'll do a few things. They might do a bit of a mask attack or brute force a small key space. Then it's like, what have you cracked? Job done, move on to the next. There is an absolute untapped goldmine of resources out there. And if I knew what I knew today, years ago, I tried to think how many extra passwords I could have cracked. I appreciate that's the same as anything in life. Fingerprint attack is the first, been around since the dinosaurs, since Hashcat started. But it's really underloved and not very much talked about. For a fingerprint attack, you don't even need a dictionary. For this attack, what you do is you take your pop file. Your pop file is a list of files of all the previously cracked passwords you've ever cracked. It's your gold mine. If I'm reformatting my box, I don't care about my personal data. I back up my pop file. Okay, this is gold dust to a password cracker. So you go through all the passwords you've cracked previously, so they're real life passwords for a start. This is just taking the clear text from that, not the hash. You expand it, you sort it, and you create a word list for the output. Now that's a very, very important part, because you can see what we're doing next. We're running Hashcat in combinator mode, which is -A1. Combinator mode takes 2 input lists, and it will mix and match every option in word list 1 with every option in word list 2. But again, we haven't started from RockU. We are expanding, so we've taken every password you've ever cracked, done this kind of crazy jazz to it, and now we're running that in combination with itself, and it creates really, really weird and wonderful candidates that normal sort of traditional word list rule attacks can't do. But the fun doesn't stop there. Whatever you crack as a result of that combinator mode, you save the output, and then you repeat and rinse. You re-expand your newly cracked passwords. Get that into a new word list after you expand and unique, and then you say it again. And what you'll find is, this technique excels on big, big, big password lists, like huge password lists, especially if you're doing like analysis on data breach type stuff, millions of hashes. And you'll find you'll very quickly crack loads, it'll plateau, and then you'll get diminishing returns hard until you get none. Either your patience or alcohol will drain first. It's hit or miss as to which it goes. A Prince pipeline, the most basic Prince pipeline you can do. Call Prince, give it a word list. We can tell Prince, set a minimum password length. This is generally almost a staple in any testing you do, because in pen testing or red teaming or just general password cracking, GPUs are fast enough that we can exhaust the key space of 7 guaranteed, 8 quite. So if there are any gamers in the house who buy the latest and greatest NVIDIA RTX cards, an NVIDIA RTX 4090 can guess end-to-end hashes at 288 billion guesses per second. Okay? So phenomenal. Stack a few of those together and you can exhaust every 8-character Windows password in under an hour. Very, very easily these days. So you want to tell Prince, don't guess 4-character passwords. I've already cracked all of them. Guess everything 8, then give it to Hashcat and append any options as you normally would. It creates really, really cool passwords. Princeception, so Jeremy Gosney, part of Team Hashcat, invented this on the fly a few years ago, and he thought, hey, why not take Prince output and pipe it back into Prince? Because why not? So Princeception felt like a very good name at the time. And again, when he was doing it, some of the candidates that came out on the screen were absolutely crazy. You couldn't even imagine them up. And yes, you are able to crack some passwords of this. I'm not going to sit here and say if you use these attacks, you're going to crack every hash. Of course, I'd be stupid to say that. But you will get hashes falling you otherwise uncontested. For anyone who's unaware, the -G at the end invokes Hashcat's random rule generation. So rather than -R for your own rule set, say, hey Hashcat, give me 300,000 completely random rules. So for this attack and the next, we've moved on to what's called non-deterministic attacks that often go for infinite runtime. We are now no longer in control of the candidates we are generating because they're being augmented by Hashcat. Netmux, who is the author of Hashcrack. If anyone hasn't bought Hashcrack version 3 from Amazon, it's about £5. Please do it. It is the gospel for password cracking. What Netmux found was, if you take RockU, give it to Prince, and just head the first 10 outputs, you'll get the same 10 candidates each time, every time you run it. But if you shuffle your input list, you get completely random passwords every single time. So we thought, oh, sod it, why not? Let's just shuffle it. Press go, walk away, and these are the types of attacks that you kind of run when you've got days and days. You've fired up an Amazon instance and you're just going to let it run. These won't ever end, okay? But they will generate, especially this one, will generate completely random candidates each time. Okay, on to delimited passphrase generation. Oh, but we're even talking about passphrases. But I'm super elite and I put spaces. I'm writing a sentence. And do you know what? That's good. You should. Any delimiter is better than no delimiter. How do we address that? Prince, we have already discussed, but Prince only accepts a single list. There is another option called Combinator X. Again, Hashcat utils. What Combinator X does, it can take up to 8 word lists. And you can see here, we've got 3 files containing 2 candidates in each one. We can tell Combinator, take that file, that file, that file, and you can quickly see what it's doing to generate those candidates. But a limitation of Combinator X that Prince overcomes is that only the candidates that are in password 1 will ever appear in the first element. So you won't ever have let me in or QWERTY appearing in this position, obviously because you're feeding it specific files. Now, if you copy and paste the same file 8 times, clearly you'll address that. But for different files, that is a limitation. So it depends on what you're after. Combinator is quite some quick wins because you can insert custom separators and different ones. Let's say I want a space between the first 2 elements, and then I want a colon, then I want a comma. You can mix and match very, very easily with Combinator. Pipe to Hashcat, business as usual. And there's an example of that in an upcoming slide. Embedded videos, because, live demos are the devil's work. So you can see here, just an example, Combinator X versus Prince. On the left, we've got 3 word lists, piping that to Hashcat, and you can see that the word the is always the first element. Now, it would eventually change if the video was, of course, left for hours, but you can quickly see how that varies with Prince, where it's randomly picking any element it can from anywhere. Prince, most of the time, is the better option. Okay, most of the time. Not all, but most of the time. And in Prince, we can also define the elements. So we've got 3 word lists here. We can say element count minimum and maximum of 3 to tell Prince exactly how many elements in our passphrase we're after. One very, very important thing with Prince, though, is with Prince we have to have a pre-delimited word list. So you can see here, I've got a combined word list of these 3, but with a space at the end. And I need to do that because Prince can't insert spaces. But in doing so, we're going to have a trailing space at the end of your word list on every candidate. And we need to delete that last, we need to truncate that last space. That's what we're doing here at -J. So dash J is a single, in this place it's applying a single rule, and a closed bracket is delete the last character. That last space is always moved. Okay, case toggling. Cybersecurity is not a technical problem. Never has been, never will be. It's a people problem. Passwords are absolutely no exception. I'm not going to sit here and say humans are terrible. No, we're generally pretty good, but we are unfortunately the vulnerability when it comes to password selection. Because humans generate passwords. And when people like to create passphrases, if you're going to capitalise a letter, you're going to capitalise the first letter. If you're doing something like this, a lot of people like to capitalise the first letter of each element because we're humans and that's what we do. Why would we go camel case or anything else? Why would we possibly do that? We are creatures of habit, and unfortunately that is our problem. Hashcat can address this for us very, very nicely. Okay, so I'll go in reverse. So Toxic 3, Yanis, who is one of the Team Hashcat members, has got an awesome rule called Toxic 3 rule, which has been in Hashcat, again, since the dinosaurs, but people don't tend to use it. And what this does is this goes through and starts capitalising different elements, depending on how many you go through, inside your word lists. You can extend that even further by using things like capital E, which in the spotted example here, with rule 2, will take any passphrase delimited and automatically just uppercase the first letter. So for a single rule, you've wiped out lots of very painful manual rules that you would otherwise had to have created. Absolutely fantastic. Use it, nest it. By nested, we means run -r rule set, -r rule set. You can use more than one rule in Hashcat. Or use it with prints as well. Have some fun. Like I said, these are all things you should be doing when your usual attacks fail. Okay, so here is the syntax slide. There's a lot of syntax, but we are talking about password cracking, so there's going to be some takeaways from this. These two options are more or less what you saw on the slide with the video a minute ago. In this first example, we're taking prints. We're saying, print, I want to crack a 4-element passphrase, denoted by our minimum maximum here. We want to have an overall total minimum password length of 8, and I'm going to give it a word list called 20k space. Now, in this instance, that's the Google top 20,000 words. For a tiny word list just for testing, it's fantastic. I've pre-appended a space to the end of every single line in that word list. Okay, that's what this denotes. We then pipe that to Hashcat. -J lops off truncates the final space to give us a nice clean passphrase. And then, business as usual, -r, and we can go on and do what we need. Prints itself comes with an optimised rule set, optimised for prints. I highly encourage you to use that, as well as other rule sets. Of course, your mileage may vary. With Combinator X, we don't have that requirement of having to pre-create our hard-coded word lists with our own delimiters. We can just pass, the word list we want, and manually insert our separators, either static or mixed, how we see fit. Pipe that to Hashcat, and then business as usual, run it with whatever you want. The examples here after Hashcat vary just because you're in your own kind of safe space now. You can do what you want after you're in this kind of zone with Hashcat. Pre-delimited lists with prints is the most painful because it does require pre-delimited lists from the start. So, for example, you would have to create a word list with one element, manually insert a space, run like combinator.bin to combine that with a second password list, and then add a space in at the end, just to create your first word list. Bit of a pain, but this does work too. Second word list is just 2 elements with a single delimiter. You can see here, I've tried to hopefully make the wording logical. Our first word list has a mid and an end space. Our second word list just has a mid space. Pipe that to Hashcat, go nuts. Who's heard of one rule to rule them all? Oh, a couple of you. Who's heard of one rule to rule them still? Oh, dedication. Okay, so that is my own shameless plug slide. So I made one rule to rule them all in 2017. I did have some people sort of say, is this going to be outdated? I said no, because I'm too lazy. It went on a bit longer, and this year I finally got around to doing it. The point of the update was not for it to crack more passwords. There are fewer rules. It's got 5% less rules, which shaved a few thousand off. What it does do is it cracks the same amount in a quicker time. This is an optimised rule set. Do not use on bcrypt, scrypt, anything painful. Use it for NT, MD4, MD5, anything in the SHA-1 and 2 family. Fast hashes, absolutely fine. Okay, when you are testing your rules, always debug. Not just to show the effectiveness of what you're testing, but also because it shows human and behavioural traits and characteristics. Again, passwords is not a technical problem like cyber, it's a people problem, and it's more a psychological study of how we're generating our secrets. When you're running debug mode 1, get that out to a file, and you wouldn't see this live, you just cat the file normally, sort, unique, and reverse it, but I'm just doing a live kind of cat on this. and you can see how your cracked passwords, the effective rules are kind of bubbling to the top. So in rules, a colon is a vanilla pass-through, just take the plain candidate. We can then see we are, in this example, comma 7 is a bit weird. That's replace the character at position 7 with position 6, and then it gets a bit crazy. Here's some more familiar stuff, $1, $2, $3 we saw there, append 1, 2, 3 to the end of your password. Okay, statistically speaking, and I'm not going to ask for names and hands, but when you've been kind of conditioned and nurtured into choosing your passwords, I'm unsecure because I've got a number and a special character. 1, statistically, is the highest performing, 1, 2, 3 closely second. For special characters, at least someone in this room uses an exclamation mark. Most people probably have. Not just because we love to exclaim our passwords as humans, no, because we're lazy. The exclamation mark is on the same physical key as 1. So 1 shift 1 saves me moving my heavy hand all the way across the keyboard to press brackets or asterisks. No, I'm a lazy human. So yeah, 1 bang, 1, 2, 3 bang. These are all very, very common things, okay? But do not make your password stronger. Please stop doing them. Okay, on to the next section, rules and buffer limits. So for this, we're going a little bit deeper into Hashcat's internals here and how the rule engine works. We have maximum password length. For a start, there are algorithm and imposed ones. LM hashes, maximum 7. bcrypt, 72-byte input. We do have fixed limitations. But when we're cracking passwords, we also have other things that are imposed on us. I say imposed, but this is actually Hashcat really helping us out there, optimizing things to make them as fast as possible for us in terms of the trade-off for computation. In attack mode 0, which is a standard dictionary attack, and using optimized kernels, -O, that most people use, and that's fine, is 31. Okay? Hard limit. If you have a 32-character hash, you're running in dictionary mode with optimized for ND5, for example. If you had the 32-character password in your word list, it would not crack, categorically, if you're running -O, because we have this limit. Okay, so what can we do knowing this? If you've got rule sets, especially rule sets you yourself have created, and I highly encourage you to do your own testing, there are things that we can optimize out that are redundant rules that result in no operations, or no ops for short. If we assume we've broken everything below 7 characters anyway, because the key space is just so small we can do it, we're talking 8 characters plus, anything P3, P4, P5, so on through to PZ can immediately get removed. Same for ZO through to ZZ. Okay, let's deconstruct. P rules. P will append the word an additional number of times. Our vanilla word is password, okay, just password. A P1 will result in password, append it once. P2, password, 8 3 to 24. P3, 4 8 to 32. We're now over our 31 limit. That's a no operation. Hashcat will only process the vanilla candidate, okay? Similarly, P2, Z7, append the last character 7 times, results in 31. Duplicate twice and append the last character 8 times, results in 32 that doesn't execute. But we don't just get password, we still get our P2. So each operation inside, they're called rule operations, and you can have a finite limit of these too. Generally speaking, there are some extreme edge cases, but generally speaking, the last op in your chain will execute cleanly if, for example, in this one, the P8 doesn't. Generally, more often than not. Similarly, in D rules, duplicate. You duplicate it once, append 1, 2, 3, we can see what's doing here easily. This one gets a bit weird though, because it says duplicate 1, 2, 3, add 1, 2, 3, duplicate bang. But what duplicate here will do in the second instance is it doesn't duplicate the original candidate, it duplicates the current buffer. And the current buffer is duplicate with 1, 2, 3. So we've got duplicate with 1, 2, 3, and then it will duplicate the entire buffer again, and this instance add final bang. Everyone okay with that one? That's the one where people just start scratching their heads and looking at me like I'm very drunk. There is methods to madness though, I promise. Okay? And again, just to kicks, we'll add another bang on to show that it doesn't execute. But it does execute the buffers differently. Okay. Oh, and also, some people ask why PZ. So you can only index up to 36 positions from Hashcat from the start. You have 0 through 9 and A through Z. You cannot, and we're going to touch on this very much in a second for this reason. That's why we have letters and numbers in there. Another interesting one, when the final length of your candidate is less than the intermediate length. Okay, so we've got no ops here that we can optimise out, make our rule sets cleaner. Here we have a rule which is prepend 1, 2, 3, okay? And we have to do this in reverse order because we're prepending. The caret symbol in this case is prepend, so we have to prepend it in reverse order. Prepend a 3, then prepend a 2, then prepend a 1. Okay, so we can run that, fantastic. We have the password of super secure 1 bang prepended. The actual final rule is here. I'm just showing it to you in stages, by the way. If we then add a P4 to that, a P4 doesn't execute, okay? So that's absolutely not going to execute. That's a long password already. We're above 31 on our limit because we're running optimized kernels. However, if we prepend 321, go out of bounds, but then truncate the 9th character, we can truncate the 9th character, and that will still execute, therefore rendering this P4 loop redundant, useless. We can optimize that P4 out. Okay. And finally, I should probably give a shout out to these rules at the bottom. See these tools at the bottom that can help you automate a lot of the heavy lifting for this. Dupe Rule's been around for ages. Rule Processor is made by Vivaldi, one of the guys from the HashMob crew, and it's a bit more modern, a bit more optimized. So I highly encourage you to do these on large rule sets that you may have in terms of your own testing and see how much you can optimize out. Okay, position buffer workarounds. Now we're going to get a little bit more crazy, but no one's walked out yet. I am both grateful and amazed. We do have some hard limits. 31 rule ops. So we're talking about each of these operations. You can't have more than 31 operations in a single rule. First hard limit. Second of all, that position buffer of 36, I said. You can't index outside of Z, position 36 from the start. We can't index on the right if we don't know where the password ends. But from position 0, we always can. We need to bear this in mind for this absolute gibberish here on the screen. Again, the last rule is actually the ultimate rule, but I'm just stepping through it for clarity. We have a password here. It's a passphrase. Sorry, it's a password. Clearly it's a passphrase with 6 elements in it. Okay, that's good. Just to show where our index bounds are, I've inserted in position 36 an exclamation mark. We can see where that hits. So, whilst we've got rules that can delete the last character, and that's all fine, what I can't do is, for example, insert let me in that position. I can't extend outside of my 36 buffer. But we can if we kind of flip the script a bit. What we could do is we could say, okay, I can't get anything past this exclamation mark, so why don't I reverse the candidate, and you can see the whole thing's been reversed. Then I'm going to insert, in reverse order, let me in, and it's a bit awkward now, I've put let me in with an exclamation mark. I probably should have done 1 for clarity. But you can see it's got let me in reverse, starting with L-E-T-M-E, exclamation mark, N, in position 6, 7, 8, 9, 10, 11, and 12. Inserting that in reverse order, as you can see, will insert let me in reverse. So why not do that, and then finally, throw another R on it. So reverse, operate, reverse again. And you can see the resulting candidate. We're getting into positions where, as time goes on and passwords get longer, this could be more of a thing. What's unlikely to be a thing in password cracking, but is definitely applicable elsewhere, is stuff like this. So passwords aren't the only thing that's hashed, okay? Domains get hashed, URLs get hashed. In game reverse engineering, internal file names and file paths get hashed. So whilst I've got a ridiculously long 97-character password here, I fully admit I've been lying to myself when I said I was trying to crack 97-character passwords. So bear with me for this example, but we can slide to the left and slide to the right. Crisscross. Okay, sorry, I tried to resist the cha-cha slide. Okay, we have first 36 characters here. Just for clarity, we want to operate on the word this. Quite clearly, we can't do that. That's outside our 36 buffer. Just to show where that buffer is again, I've done an IZ bang to show you where that exists. Okay, let's slide to the left a number of times. Is that 13, 12? I don't know. Either way, you can see the password has been slid to the left and then effectively appended onto the end. It starts here. Now, the word we want to operate on is within positional bounds. I can insert a position 35, replace the character at position 35 with the number 1 to change this into a this with a 1, and then slide to the right. And here we are back again. Like I said, less applicable in passwords, granted, but definitely applicable in other areas. Markov chains. Who's heard of Markov? Oh, look at the hands. Okay, who wants to get up and teach it then? That's anyone? No? Okay, awesome. TLDR, statistic probability of output of a character based on the preceding character. It's kind of like if you've got a Q as the starting letter, there's a high chance the next letter might be a U, for example. Through years of password breaches and stuff, we can see the types of characters people choose and the types of characters that people choose afterwards and after that. And we can build these up. These are called Markov chains. Now, Hashcat, by default, a little lesser-known fact, uses Markov based on Rocky by default. So, Hashcat will never, unless you tell it to, do a completely naive, unintelligent brute force, as in A through Z, AA, AB, AC. That will never, ever happen. Because Hashcat, like John the Ripper and other tools, will actually help and do this for you. But what if you want something more targeted than Rock? I mean, Rock is great, but it was a breach in 2007, and there are better lists out there, which I can talk offline about. But it's the one everyone knows, so we have to tick the box. Let's say I've got in possession a Minecraft breach. And actually, the Minecraft breach from the Lifeboat community in 2016 was one of the corpuses I used to develop one rule to rule them all, funnily enough. So this was a breach. But if you've got a Minecraft breach and you're an attacker, I reckon that loads of the passwords inside a Minecraft breach might have passwords that are Minecraft related. That would be reasonable to assume, right? Yeah, surely. There'd be loads of kids making passwords about Minecraft stuff, obviously. Okay, so maybe running Hashcat with its inbuilt default Markov table is actually going to limit it somewhat. Okay, we can work around this. You'll never know if this is good until you tried it, of course. But what we can do is we can say, right, and what I did, because the stats I'll show you in a minute are real, I went online to a Minecraft wiki, and I downloaded a list of every Minecraft object, monster, like my kids love Minecraft, I should pay more attention really. Every Minecraft object in the game I could find. I don't know, it's probably a few, 500, 600 maybe. I then mangled that with my rule, fantastic, to get a really, like tens of thousands, a really mangled list of passwords that are all based on real Minecraft things, shall we say. Created a list out of it, stage one. Next, Hashcat utils again. HCStat to gen. This is a tool, a binary for generating custom Markov tables. I gave my resulting password file to HCStatGen2 and generated a file, HCStatGen2, which then, just due to Hashcat's support requirements, needs to be compressed. And when that's in a format that you've got ready to go, you can then pass that to Hashcat with the -- Markov HCStat2 switch. So now, Hashcat is not going to use statistical analysis based on RockU to do its per position Markov modelling. And you can see here we're doing a brute force. In this case, we're only doing 7 characters because I have a Lenovo ThinkPad, and when I'm cracking properly, I do not use that. But for this example, it's on that with a real GPU. And what we found was, if I ran it, this is 60 minutes runtime, just an hour. In an hour, using just RockU, just Hashcat, I cracked 12,000 less passwords than when I supplied it my own custom rule. And all I did was scrape a couple of wikis and then tell Hashcat, look at all these passwords and do some analysis based on the probability of the sequence of characters and use that to do your intelligent brute forcing for me. And in 60 minutes, we cracked 12,000 more passwords. Okay? So for targeted breaches, for targeted attacks, where you've got big custom word lists, don't overlook custom Markov. Okay, Unicode. Oh, the fun of Unicode. And emojis. Woohoo, we all love emojis. Shout out to Yanis, who did a talk at DEF CON this year. I literally, as soon as the talk was over, I found him and I applauded him. It was brilliant. Just a one-liner to print out various Unicode code points. So now we're talking about outside that nice, comfortable ASCII area. There have been times, not many, where I've needed to crack an Arabic password or a Greek, or the hardest ones are always the Asian-based languages, like variants of Chinese and things. It's absolutely horrible. But all of these things fall outside of ASCII. They're all what we call UTF-8. So what we can do is go to a UTF-8 table, millions of them out there. In this example, we can see the code points for Arabic are 0600 to 06FF in hex. Okay, so 0600 to 06FF, which I think is this second example here, and it will just print out all the Arabic characters to your screen. Fine, easy. Do that for your language of choice. For emojis are a bit more painful because emojis use up to 4 UTF bytes per character, which is a pain. You can see in this example, Arabic uses 2. So the Arabic number sign, whatever that is, uses D880. Okay, so for ASCII, we've got 1. For UTF, we have up to 4 bytes of encoding, depending on what we're targeting. Greek and Arabic use 2. Emoticons use 4, and there's many others. Either way, we need to show how we can create these symbols to set the scene for further attacks like this. So Hashcat, again, our saviour, does accept Unicode characters to stand in. In the top example, I've literally quoted all the Arabic characters and then created a mask from my custom character set that I've created here and say, attacker 2468 character Arabic password. Please do bear in mind, in this instance for Arabic, it takes 2 bytes to represent a single character. So that's only going to be 4 Arabic characters, because 2 of those bytes is going to be a single character. And you can, absolutely, crack Arabic passwords. What the hell not? Windows has had UTF-8 support in beta for approximately 700 years, give or take 1 or 2. If you go into your regional language settings and go to advanced, you can do enable UTF-8 support beta. And it's quite useful for this kind of stuff. Or we can crack in hex as well. And if we're doing it in hex, we need to give Hashcat the hex charset switch so it actually processes these as hexadecimal. And if you were to go to this site or any site and look for emojis and look at all the examples of 4 byte combinations. For emojis only, the first byte is always F0, the second byte is always 9F, the third byte could be one of these 4 there, and the fourth byte could be any of that. So again, reduce our key space, make sure we're only testing combinations of things that do actually exist. And in this example here, we've got 1, 2, 3, 4, 4 times. So that would crack a password that contains 4 emojis in this instance. We can also use Unicode in rules. We have to escape the X with a backslash, prepend, append, do whatever you want, prepend and append. You are going to run into limits as to how much you can do before you get various errors that are all there due to how many values we can store in 32 and 64-bit integers. But it is fun, it is good, and people really do use them. I'm not joking. Yes, I'm not going to see this on a pen test. If I've done TD, I'm not going to be seeing this stuff because people aren't going to be typing this on their keyboards. But you do see it, even on outside of Active Directory environments, people like to copy emojis on their desktop computers, let alone people generating accounts on their mobiles. Oh, of course, Wi-Fi, SSIDs with emojis popping up. People love emojis now, everything's on mobile. So this stuff does happen. This is real data. I've not forged this, okay? These are passwords. Okay. I need to calm myself down. I'm getting a little bit too excited. I apologise. I really love passwords back here. Okay, Temesis. So Temesis is an insertion rule generator again. Hashcat utils. Thanks to Royce Williams, who goes by Taisha Tithnis. I DM'd him a few months back and he actually put in a pull request and then, well, he made the addition for me to allow Temesis to support UTF-8 characters, because before that he didn't. But it's fantastic. And what this does is it generates this. Okay, it doesn't generate that. That's the crap. It generates this. So you give it a word list, and it can splice one word list in with another to generate candidates like this. And you can see the word password here, for example, is being shifted through 1 through 5. There are limits to that, unless you want to muck around with the Perl. You know, it only goes up to 15 positions, and there's other kind of limitations. But this, which I'm not allowed to give you the code for, but Yanis promised me, it's going to be either in Hashcat or Hashcat utils very soon, for just single list insertion. So you give it 2 word lists. I mean, you could write your own. I mean, don't get me wrong, this isn't black magic. Not to discredit Yanis, she's done a fantastic job. But yeah, give it a word list and it supports Unicode, and you can just see what it does. And then, when you've got passwords like that, give that to Expander, give that to Print, give that to Expander, and then expand it again. Honestly, you go so far down the rabbit hole, you will never see the light of day again. It's absolutely phenomenal. Nothing gets me happier at 2 in the morning when I'm high on coffee than watching some of these random password candidates come up with all manner of crazy passwords. And if in those lucky elusive times one actually cracks, yes, my kids get woken up at 3 in the morning because I can't suppress the screens. But yeah, use your imagination. For those of you who haven't heard of Expander and Print before today, please start using them. And if not, and if you need help with them, please DM me. I mean, everyone's got like Twitter shout-outs here. I am more available on Discord. If you want help, happy to help you. Right, I like this one. That looks like a pretty good password, right? Everyone's smiling at me because they're seeing a bear trap being laid, and you're damn right. Hands up if you think you could crack this password. Of course you're not going to put your hands up. I've just set the trap. No one's going to actually admit to be able to crack that. For all intents and purposes, you've probably counted the number of characters in there. That's not a terrible password. Societally speaking, based on how we choose our passwords, like right now, summer 2023 bang is being used, autumn 2023 bang, seriously, I kid you not. For anyone who's seen the film Snatch, Vinnie Jones, never underestimate the predictability of stupidity. Honestly, I'm not going to tarnish humans with a brush, but there are times where I'm sorry we should not be using the season and the year. Rant over. That would look like a pretty good password for all intents and purposes. But would it surprise you to know that if you took the NT hash of that ASCII string there, I want to tell you that it appeared in 249 data breaches in Have I Been Pwned password list. That's an alarmingly high number of data breaches for that string to be inputted, right? Yeah, no one's got their hand up now, have they? That's because that is actually the transliterated password for my password when typed into a Zhuyin keyboard layout, which is very popular in Taiwan. So Taiwanese users who are typing my space password will type in those characters. And if you go to an online Zhuyin keyboard layout, you type in JI and it'll present you with 27 different tones for that one letter. Honestly, it was absolutely mind-blowing. But yeah, it spells it out. But this is actually a big deal because it's the transliterated password that's hashed, not the Unicode character. So yeah, you see this and you just think, oh yeah, I ain't cracking that. But this is actually a really, really important thing, especially if you're targeting passwords outside of printable ASCII. And it also raises the very, very important question, and one I often get asked of, but hang on, password entropy is everything. If it's got good entropy. Well, yes. Okay. Blanket caveat, I am not debunking entropy. Entropy is good. Okay. No, seriously. It's scientifically good for computer-generated passwords that are absolutely 100% completely random. Completely random, okay? The fact is, a lot of the time, passwords aren't random. And for people who know about sort of PRNGs and CSPRNGs, with the distinction between that as well, unless it's a reputable, it's a ratified CSPRNG, password managers, whatever you want to target, it's not actually good. Let's take the entropy of this. Entropy is log base 2 of the key space. 36 characters are set there. We've got lower alpha and numbers only. 36 possible characters. Raised to the power of 12, the length. That gives us, with the log 2, 62 bits of entropy. I've seen worse. We've all seen worse. That's not terrible. But whilst that's fine mathematically, societally for us, entropy is quantified by how a password looks. You look at that and you think, yeah, that's got good entropy. Look at that, 62 bits, yeah! No, cracking that. But this is kind of a counter to that. Because, that actually isn't the best password, if I'm really honest with you, for reasons we've just shown, okay? So again, not debunking entropy, but entropy assumes that it's a completely computer-generated random attack, which, give or take, 0 people do. Because no one goes A, B, A, C. No one attacks like that. Because all the tools you use Markov. They're helping you, whether you know it or not, your tools are actually giving you the college try. They're giving you the fighting chance to really get those passwords where possible. No one uses Markov disable. Test it for yourself. Hashcat-A3, D for a number. Run it by itself and it will print like 0, 2, 1, 9, but it won't go 0 through 9. Run the same command with Markov disable and Hashcat will print 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Hashcat is doing a lot of the heavy lifting for you, okay? So I'm not here debunking entropy. But we have to make sure we're addressing and talking about entropy in the right context when we are talking about completely random passwords, which are actually rarer than you might think, okay? Because when you get into areas like this isn't actually a crazy password, okay? I realise I probably opened up Pandora's box now about cracking emojis, Chinese characters, and everything else. So I'll mentally prepare myself for whatever weird and wonderful questions you're hopefully not going to ask. But let's move on to the last part of this, hash upgrades. Okay. You're responsible for an app. You've developed an app. You've been using MD5 since forever because you're 72 years old and MD5 was probably just around when you started using it. Fine. You want to upgrade the security. What do? Do you reset all your users' passwords? Okay. Do you update your passwords and upgrade to bcrypt, for example, on the next login, requiring you to store both hashes? Do you rehash the hash? Okay. So, see, I told you this isn't my laptop. That arrow is, of course, in the gap there on my laptop. Okay, here's an example. An absolute token shout out here to Sam Crowley, who goes by ChickenMan512 on Twitter, but on Discord is just ChickenMan, one of the core Hashcat developers, who did a fantastic talk in DEF CON a couple of years ago called What the Shuck. We're building up to something called hash shucking, which we're now kind of setting the tone for here. So, you've got an MD5. Let's say you want to upgrade your database by bcrypting your MD5. In this example, we're taking in security, MD5ing it, we're then bcrypting the MD5 value, and here we have a result. Hashcat supports bcrypt of MD5, no issues there, and we can still crack that to get the play at the end. No problems at all. But let's speak about this adversarially in a real world and how a threat actor might go to use this against you. We have a user here, a happy-go-lucky user who's created a pretty good, absolutely not uncrackable, not at all uncrackable, but a pretty good password there. User, because we're humans, has reused that password on site A and site B. I'm seeing some nods in the audience already. You know where this is going. Site 1 hashes Bob's password. It's always Bob and Alice. Bob's password with SHA-256 of the string. Fantastic. Site 2 bcrypts a SHA-256 of it. Okay. These two sites get popped. Okay, an attacker now has both of these. If an attacker is able to go through an uncracked list of SHA-256s, for example, they might have, bcrypt each of those values and generate the resulting hash, they don't know the clear text password, but they do now know the SHA-256 of the password that was used in the bcrypt process. Oh, I'm seeing some okay. I'm seeing some nods. Okay, awesome. Which means this is brilliant news. Because we don't have to worry about running like a dog with 3 legs on bcrypt. We can actually get out of bed in the morning and actually crack some hashes, because SHA-256 cracks a lot faster. That's based off an RTX 3090 for anyone interested in the benchmarks there. Yeah, for anyone who's ever cracked bcrypt, no one gets out of bed for hashes when you've got the shadow file. Yeah, great, fantastic. But bcrypt is really, really, really hard to crack. It's very, very GPU resilient. We'll touch on this again later, okay? And that's even with the default work factor of 10. You could increase that, and there's currently an RFC to increase the default iteration count, work count of bcrypt from 10 to either 11 or 12. So this is very, very powerful because people who are in possession of lots of data breaches can do this. They don't need to know your Plaintext password. They amass enough uncracked hashes of a type they're able to identify. And there's 100 ways an attacker could identify that. They could look at Have I Been Pwned. They could read a blog that said, oh yeah, XYZ that got hacked. You bcrypt the MD5. Fantastic. I know how that was generated. Let's find every MD5 I've never cracked and bcrypt it to see what there is. There's 100 ways this could go. But if the inner hash, okay, in this case SHA-256, is very fast because we want speed increases, and it's unsalted, very important, because the attacker wouldn't have knowledge of the internal salt that was used to generate, we can shock off the bcrypt in this instance, shock it off, and then there we go. We've now got the inner hash, the SHA-256, or the MD5, or whatever it might be. But, Will, I'm not a bad guy. I don't do this. I'm a pen tester and I rinse AD day in, day out. Well, that's good. Luckily, we've got you covered there. I say we. I take 0 credit. The clever team at Hashcat have done it. This was a beta version that I used. This has now been pushed to main branch. So don't run the binary. If you're compiling Hashcat from source, you now have all of these modes in. Domain cache credentials were recently added, so you would have this. Commonly, for pen testers in the room who all love to go in, like me, in the morning, you've got a man in the middle 6, you've got responder. The only 2 commands you've ever used while you go to get your first coffee. You come back and it's rained hashes on your screen, or you've relayed off to 20 servers and it's happy days, DA in an hour. Okay, great. But what about those hashes you don't relay? Those NTL MV2s you don't crack? Well, when you peel back all the layers in Windows world, everything's an NT hash. Everything's NTLM under the hood. Okay? NT is used to encrypt service accounts during curve authentication. NTLM, challenge response. The NT hash is used to encrypt the challenge. NT is everywhere whether you like it or not. So what I'm saying here is that when you are dumping NTDS, when you are running your AD ransacks, whatever you don't crack, never delete it. And I'm hoping everyone's going, oh no, all the millions of NT hashes I haven't cracked that I've got rid of. When you're done, dash left and output those you haven't cracked to a file. Treat that like your pot file. Don't delete it. Every NT hash you don't crack, you could use to crack an NTLMv2 in the future. Now in Windows world, this is actually brilliant because even if you don't know the clear text password of whatever this is, that's fine. But once you know the NT hash, you can pass the hash, business as usual. The hash is as good as a password for Windows. So this is actually really powerful. And again, not an attack I'm saying is going to allow you to crack every NTLMv2 straight away. Of course it's not. You need to amass a file of uncracked NTs first. But this is literally cracking hashes with hashes. You don't know the plaintext, but you can attack the underlying hash that was used to construct, in this case, NTLMv2, or the cache domain credentials. Okay, hopefully that was a bit of fun for everyone. So, we're going to wrap up on something that actually isn't password cracking, but it's kind of like the whole, oh, so what should I use? Yeah, okay, go to OWASP, that's fine, that's great. OWASP recommends in order. Argon to ID with some memory requirements, iterations, single thread, great. scrypt, really memory hard algorithm there. And bcrypt with a minimum of 10, that's good. Now, bcrypt is an unintentionally cache hard algorithm, okay? For anyone who's done password cracking, like in a bit more depth, you might have heard things like scrypt being memory hard, okay? It's a memory hard algorithm. Bcrypt is unintentionally cache hard. Now what that means is if we can keep the hash in level 1 through 3 CPU cache before it spills over into RAM, which is where GPU acceleration comes into its own because we need memory to do GPU stuff. But if we can keep the hash on the CPU before it spills over, this is pretty good. We're talking defensively now. This is like good protections, obviously. This is really good. It's unintentionally cache hard. Now, it's better than memory hard algorithms, and there's good examples of this, but only for real-time authentication. Now, real-time authentication is generally denoted to be a second or less. Under a second is considered acceptable for real-time auth. So, in the examples of scrypt and Argon 2, for runtimes of less than a second only, bcrypt is better. Of course, there's going to be a point where there's a meet and a changeover, granted. Which is why these two algorithms, which are very memory hard, are good for general key derivation function work, good for KDFs, but not for real-time authentication. But then, for those of you who might have looked into this a bit further and said, well, hang on, there's loads of cache hard algorithms, there's bscrypt, there's pufferfish, there's really good cache hard algorithms out there. You're absolutely right. but they are newer, they're less studied. Bcrypt is Bcrypt. We know about Bcrypt. Bcrypt's ratified, tried, tested, and it's good. And it's probably one of the reasons, I haven't asked him, maybe I should, why Jeremy Gosney kind of coined HMAC Bcrypt just over a year ago, which I'm really hoping is going to get the uptake soon it deserves. So this pre- and post-hashes using HMAC SHA-512, and it uses, it's an optional pepper, but people are generally using a pepper. Pepper instantly means it can't be shucked. Brilliant, fantastic, job done. That's then base 64'd, it's then bcrypted, and then it's post-hashed again using the same process. This overcomes broken implementations. This overcomes the 72-byte length limit that Bcrypt natively enforces. Unfortunately for us yet, our tools don't support HMAC Bcrypt, but Hashcat does support Scrypt, and John the Ripper does support Scrypt and Argon. We'll get there soon. Okay, I've got this in because it's free. If this was commercial, I would never be plugging it at all. We used to have a commercial training course called Password Cracking 101 that we ran with Black Hills Information Security. We decided June last year to make this free. It's got a VM to download, pre-built with 15 hands-on challenges and answers, 15 YouTube videos of my dulcet tones over about 4 hours, maybe enough alcohol will get you through to the end again. It does cover, not everything we've covered in this talk, but it certainly goes into UTF, custom masks, combinator, prints and other things as well. So if you haven't, if you've not been enough glutton for punishment already and you're feeling a bit more sadistic, please go to the free site, go to our website here. Like I said, there's loads of free training on there and you can go nuts. I think everyone might be a bit too scared now, but if you want to win a coveted insecurity challenge coin that glows in the dark, you heard it here, folks. Only a hacking one, I'm afraid, because we're currently out defending ones. If you can crack that hash, and the only hint I'm going to give you is, if anyone's heard of checklists, Daniel Miesler's top 100, but you need to think creative. If you can crack that hash, and I would say tweet me, but quite honestly, find me on Discord, because I'm more likely to see it. You can win yourself a coveted, priceless insecurity challenge coin. But on that note, always be cracking, okay? Thank you very much. And for anyone who still wants more, we had a password CTF that I released in 2018. The cryptocurrency prize is gone. Don't think you're going to get any crypto. It took someone 4 hours to swipe it. We put $100 of Ethereum into a wallet. But all the details are there if you want to keep the fun going and the coffee drinking. But yeah, apart from that, does anyone have any questions? Yeah. I don't know who was first, but go on, sir.
So with people using passphrases, maybe they would select a passphrase from a book. So assuming you had the text of a book, what would be a good way to turn that into a cracking list? So
for a targeted attack, you'd need to kind of have an idea of the book that someone's used. There are alternative methods like one-time grid. There's also Diceware. Diceware's been popular for a while and still is. So for those of you who aren't familiar with Diceware, you've got a choice of 7,776 words, and you literally roll dice, and you choose 5 random passwords, the key space of which is computationally secure in terms of exhausting a key space. With a book, again, if you have knowledge of what that might be, if I was targeting you and I saw on your Facebook, LinkedIn, Twitter and Insta that you loved Watership Down, maybe I'd index Watership Down and use that. Adversarially in terms of real life, I've seen it a lot in competitions. But you'd have to have pretty good knowledge of what the original purpose was.
You knew the book. I'm thinking like a sliding window, but it would be variable length because you wouldn't know how long the passphrase is. I was just wondering if there was a tool already.
Yeah, so what you would do for that is if you thought it was a passphrase from a book, you would use an example from an earlier slide. You would probably use this one near the very beginning. You'd probably use this. But you'd need to augment it a little bit because you wouldn't necessarily be starting with a mask. In fact, there's probably a better way of doing this. Let's take this one. Forget the rest of it. You would index your book, create a word list out of it. You give it to prints. You'd say element count minimum 2, element maximum count 5, 6, whatever you want to. And then it would concatenate and create 2 to 6 element passphrases you know in terms from your book. If you use print to do that and then pipe it to Hashcat, you could then run rules to augment that even further, which possibly people have done, O to 0, L to 1, the usual crap we all use. But that's definitely the way I would do it. And then you can explicitly define how many elements in your passphrase based on your book's corpus. Yeah. Emojis.
Yeah, of course. Basically, I noticed that in the chart that you have real data with emojis cracked, it seemed like there's a bit of a pattern to it. So is there anything
That's only because, and I've got no email addresses in this or anything actual personal. Obviously, I've looked at the passwords themselves. That's only because the examples I've used, I made a prepend list only, an append list only, and in this case, prepend append. So it put an emoji at the start and end of each one. So in the ones that I cracked here, they were only ever going to crack if there was a single emoji at the end, just in terms of the demo. You could augment that out further and use multiple emojis.
So the question is there any research or any kind of data on how emojis actually are used?
Quite possibly, but I wouldn't.
Okay.
That's more you're actually like the more the human study of how they're used and selected. I would almost certainly say so, but I wouldn't know. I'm afraid I haven't seen anything myself. Yeah. Oh, I've got 2 minutes. I'll do 2 questions. I'm getting all excited. Oh.
Oh, okay. Then how do I get out of it?
Hey, you can't. That's why I'm using Nano. I'm not a real pen tester. God, real hackers use Vim. No. Yes.
So if I use KeyPass to generate a passphrase with 6 words, is that not good enough?
That's probably good enough.
Oh, okay.
That's probably good enough. Now, when you say use KeyPass generates it, or you put 6 words into KeyPass.
No, KeyPass is it.
Oh, so a sufficiently entropic password. Yeah, you're probably good.
Okay.
You're probably good. However, KeyPass XC still has a current issue. The ClearPass data, the ClearPass master password is in RAM. Not KeyPass, KeyPass XC. You might have even seen the tweet. Yeah, okay. It's from Snow Crash. Yeah, it was a couple of months ago. But it's still there. I tested it on the most recent release. KeyPass itself, though good, it uses decent algorithms. And is the default iteration count 30,000? Or has it gone up? I can't even remember. It's painfully slow. You're not going to get out of bed for a KeyPass hash. You're safe.
Thanks.
All good. Anyone else? Yes.
You recommended the book quite early on.
I did.
Can you write it down?
Hashcat. Its current version is version 3. It's on Amazon. I think his name is Joshua Piccole. I think his name is. He goes by Netmux online. Really, really good. It covers loads and loads of stuff. Like lots more than I've course covered here. Well worth it. Yes.
The special character set includes a $sign, but on my UK keyboard,
Yep.
I have a pound sign.
You do?
Pound sterling.
Oh, yeah. So
Is that going to be catered for easily?
so it can be catered for, but it's a very valid point. So a UK pound sterling sign is it's like a bit of a holy grail, because the UK pound sign isn't part of the 95 printable ASCII characters. A dollar is, but a pound isn't. You have to spill over into extended ASCII for that. So you could attack it 100%. But by doing a question mark A, for example, or a question mark S when assigning masks, you are not going to cover that key space. No. So you'd have to augment the attack and then include that custom character. Yeah.
So you mentioned the default markup model that Hashcat uses.
Yeah,
to
okay.
train on one cube, right?
Yeah.
Are there any markup models out there that are based on like Chinese characters?
That's a fantastic question. I'm willing to say yes, but quite honestly, Yanis is the person I would ask about that, because he's literally just done a talk covering that. So there are, but if you download Hashcat Legacy has lookup tables called simple table.plb, and you can use it to do lookups of UTF. Yeah, to match stuff already to get that transliterated output. So in the example we had down here, you can do that kind of thing there, where you can actually work out what that might be based on a Zhuyin or Mandarin or whatever it is you're looking at and that kind of thing. But I'm not aware of this resource as a fantastic markup for Chinese work. Asian-based passwords, they love numbers. They love numbers. Chinese people on the whole, 1 through 6, like repeated numbers. For some reason, again, psychological study based on Asian culture, who knows, they love numbers, which in itself is fantastic when attacking a really reduced key space.
See how different like languages, cultures.
Yeah. Well, that stuff fascinates me too. Probably more so from a how to attack it kind of point of view. But yeah, it's really, really interesting culturally how we select our passwords differently. I'm over time. Everyone, that's enough, thank you. But please find me afterwards and I'll happily bleed your ears more than I already have.